The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hello, welcome. As you expect, the big news is that there's a quiz next week. So hopefully that's all square. Everybody knows everything. Questions, comments? Everybody's pretty comfortable with what's going on with the quiz? If you have a conflict, please contact me shortly because I have to arrange rooms and proctors. No questions? Good. So last time we looked at discrete time frequency responses. Lots of things were similar. A few things were different. The first difference we saw was that in discrete time, we like to think about complex geometric sequences rather than complex exponential sequences. And the effect of that is that the frequency response lives on the unit circle. So if you try to think about a discrete time system, say, characterized by a Z transform, and think about what would be its output when there's a sinusoidal input, just like CT, if you have a sinusoidal input, there's going to be a sinusoidal output at the same frequency. But the amplitude and phase can be shifted. But to compute the amplitude and phase for a DT system, you look at the unit circle of the Z transform. That's as distinct from the Laplace transform. In CT, we looked at the j omega axis. So now everything we used to say about the j omega axis, we say about the unit circle. Other than that, things are extremely similar. And just to boost your confidence that you know exactly what's going on, here's a question. What if I gave you a system that had a single pole and a single zero, and say the pole and zero are related that way? How would you think about that system? Low pass, high pass, all pass, band stop, high stop, low stop, all stop? So some very early votes that are completely correct. You had it in recitation, so then there's no excuse. So if I see any wrong answers, and I see wrong answers, ah! So maybe I should have the recitation instructor. Well, no. Okay, everybody votes. So high pass, low pass, band pass, all pass, band stop. None of the above. Vote. Okay, the vast majority is 100% correct. The vast majority is correct, but it's not quite 100%. So the answer is 4, all pass. Why? Can somebody make an argument why that should be all pass, other than you saw it yesterday in recitation? I mean, that's a good reason. Yeah?
If you go along the j omega axis for low omega, the magnitude of 0 divided by the magnitude of the pole is pretty large. And then as you go up to infinite omega, it goes to 1. So everything's going to pass.
So I'm a little bothered by infinite omega. Where should we be? When we think about things as low pass, high pass, whatever, what are we thinking about when we say something is a low pass filter? So somebody says this, so what's that mean? That's correct. So a large fraction of this class is learning to interpret sign language in the air. So what's it mean if a system is low pass? What do I look for when I look at this diagram to see that something's low pass? Where's low frequencies on this diagram? Cut it in half. Cut it in half, top and bottom. Take that side. So low frequencies are there, right? So we're thinking about frequencies being e to the j omega. right? Because what we're thinking about, we'd like to think about cosine of omega n, but we want to make that look like an eigenfunction. So we want to make that look like e to the j omega n plus e to the minus j omega n, that kind of thing. That kind of thing, okay? And divide by half probably. Okay? So the question, so this is all pass, and that's actually kind of tricky if you think about how it would become that way. Yes?
I think at any point on the unit circle,
yes?
the distance from the 0 to that point is exactly 8 times the circumference.
That's precisely right. So somehow, if you took this distance and that distance, which is intended in this figure not to look the same, but if you took the ratio, because this one's a 0, so it's in the top, and this one's a pole, so it's in the bottom, and if you took that ratio, somehow, if you took that ratio divided by that ratio and compared it to this one divided by that one, those numbers would be the same thing. That's what would have to happen, right? You would compute the frequency response, the magnitude of the frequency response by taking the ratio of the magnitudes of the angles, the magnitudes of the vectors that connect the 0 to the point of interest and the pole to the point of interest. The point of interest being on the unit circle. Okay? It's not at all obvious to me that that ratio is a constant if you move around, along a circle. That's another one of those things that I think I need a Greek to convince me. Oh, somebody knows. Wonderful. So you should explain it to me. Putting you on the spot. It's okay. If you want to, that's fine.
So if you have any point on the unit circle,
Yep.
you draw like a line from that point to the origin.
So if you have any point on the unit circle, say that one.
Yeah, so you draw a line. Actually, you do it on the other side, on like the second coordinate.
So you like this side better, okay?
So you draw a line from that point to the origin.
Okay.
You also have like your 1 over a and a on the x-axis.
So 1 over a and a.
So you also draw lines from those to the point of the unit circle.
Up here?
Yeah. So now like you have two triangles that have like the same side and the same angle. And like if you just use the law of cosines.
You have two.
So you have like the big triangle and the small one.
So we have this triangle and we have this triangle.
Yeah.
Those are the two you want?
And yeah, so like they have the line on the leftmost is like the same for both, and like the angle at the center is the same for both. And
So this angle is equal to this angle?
No.
No.
The central angle. The central angle of the. It's.
They take the whole big triangle.
Take the big triangle
And then the one with just the angle at the origin.
and the angle at the origin.
So that angle is in both the big triangle and
That angle is in the big triangle and the little line. Yes? Got it?
And like the sides at the bottom are like 1 over a and a for the two triangles.
Yep,
So
yep.
like you just use the cosines and.
That's very good.
Isn't that pretty?
Was that?
Isn't that pretty?
That's amazing. So, wonderful. Congratulations. So, you're also working on the triangle thing? Don't have that yet. Okay. I'll keep checking in. So, the way people who don't do quite so well in trig do it, so you can also just empty-headedly substitute z equals e to the j omega. And then if you want to make the top look a little bit more like the bottom, you could take out the e to the j omega part. And then you see that these look like complex conjugates. Okay, so this is kind of the math way, and what you said was the trig way. I like the trig way much better. The plain G way, yes. So complex conjugates, same magnitude, done. Okay? Okay, so the whole point was just to motivate the idea of thinking about an all-pass. Why would you build an all-pass? What's an all-pass good for? 6003 exercises, of course. So an all-pass doesn't change the magnitude, so what's it good for? Changes the phase. So if you were to think about what's the phase of the all-pass, you get a function that depends differently, right? So you would have, so you have to compute the angles of these vectors, right? So this one, the angle at the 0 starts out at pi. The angle associated with the pole starts out at 0. There's actually a minus sign in here because I took 1 minus z compared to z minus a, right? So I put the z at the two places, so there's a net minus sign in the whole transfer function. So the pi cancels out the pi, so we start at 0 at 0. Everybody know what I just said? So the angle associated with the 0 is pi, but there's also a negative sign associated with the transfer function, because we would normally like to write z minus 0 divided by z minus a pole. And I didn't write it that way. I wrote the top one I wrote backwards. Okay, so there's a net minus sign. Because of the net minus sign, the phase starts out at 0 instead of pi. That's how that got to be 0. So this starts out at pi, right? The angle starts out at pi. It becomes less, and then it goes back to being pi. But the angle associated with the pole starts at 0 and goes around the pi. So the net from the pole is a pi shift, which accounts for why this goes from 0 to minus pi. Okay, you can all do that, right? So the idea is that the all-pass would alter the phase, and that's one of the things I wanted to talk about. What's the effect of changing the phase? And I'll do a demo now thinking about how it affects audio, and at the end of the hour thinking about how it affects video. So to think about this, I took this fraction and I used a equals 0.95. And I took a waveform that I generated with Python. I just added together 3 tones in the ratio 1:3:5 in frequency, so it would sound somewhat harmonic. And when you add those together, you get a sound like this. What you hear is a very dominant tone, a very dominant pitch, because I made the harmonics be integer multiples. So I made the overtones be integer multiples of the fundamental. So the fundamental was A440, and I put in some third harmonic and some fifth harmonic. So you get something that sounds very, very constant pitch. Then I took that waveform and put it through this filter, and that changes this looking waveform into that looking waveform. Those are real waveforms. And then it changes the sound so that instead of sounding like this, it sounds like you can all hear the enormous difference, right? So even with headphones, I can't hear any difference at all. And that's kind of a property of the way you hear. You kind of hear. I'll say some caveats about this. This is not exactly true. So Ohm's law of hearing, same Ohm, says that you hear sounds by the frequencies that they contain. Roughly speaking, you hear sounds according to the magnitude of the frequencies that you hear. Now, that's not quite true, but it's sort of true. So let me do a more complicated example. So the first sound is a consonant vowel consonant.
That.
And then I put it through the same all pass, so I screw up the phases. So it goes from looking like this to looking like this and sounding like
that.
Okay? Hard to hear the difference. Here's an even more complicated sound. This is Bob Donovan's thesis. Put that through the all pass and you get
I must apologize for speaking on a monotone, but you see, I have no brain.
If I listen to that on headphones, I can actually hear a difference, right? But I study hearing and I know what to listen for. So it's still difficult to tell the difference. Now, that's because I kind of cheated. To let you know how I cheated, let me do something more drastic to the phase. Let me play the waveform backwards. Now, you could probably hear the difference. Okay, so now check yourself. How does the phase of the second signal compare to the phase of the first signal? So look at each other so you can blame each other. You know, if you work on this in solitaire, then I'll have to blame you. So what's the phase relationship between the x signal and the y signal? If I showed you the Fourier transform for the x signal and looked at the y signal, which is x of minus n, how would the two look the same or different? I sort of gave it away. Flipping in time does what to the magnitude of the Fourier transform? Flip in time doesn't change the magnitude at all. What does it do? Flips the sign of the phase. That's exactly right. So, you know, if you're into mathy sort of things, you can think about representing the two as Fourier series, the AKs and the BKs. And if you think about what happens if you have x of minus n, you can do a change of variable, make that look like x of n, then it looks more like the Fourier series equation, except that now I lost my minus sign. So a sub k is the same as b sub minus k. The effect is to flip the sign of the phase. Why would that be so much more audible than the other things that I showed you? Flipping the sign of the phase, why would that be audible? What would it mean if I flipped the sign from 68 degrees to minus 68 degrees? Not a clue. Yes?
For cosine, it wouldn't change anything, but for any of the sine terms, it would invert.
So it would invert. Right, let's see, if you went from plus 68 to minus 68, so say I had cosine of omega n plus 68 degrees and cosine omega n minus 68 degrees. So I changed the phase by flipping the sign of it. How would that change the relationship between the two signals? What's phase? Intuitively, what's phase? Yeah, it's this way, right? It's time shift. So the problem with this phase shift is that you're shifting all the different components by different amounts of phase. So you might have a little bit of 68 hertz and 72 hertz and 3 kilohertz and 512 hertz, and all of those are getting their phase flipped. So whatever it came out, 13, 128, whatever, it becomes minus that. All of those phase shifts represent a time shift, right? All the components are being shifted in time. So you're shifting around things, all the different components, by some amount. And what your ear is actually very sensitive to is the low frequencies. When you shift the low frequencies by an amount of phase, that's a big time. So if you think about the fundamental frequency that started when the utterance began and went to the end of the utterance, that was like 2 seconds. So whatever that phase is, it got inverted, which is a large fraction of 2 seconds probably. You can easily hear a time shift of 2 seconds. Yeah?
Could you notice if it was just a pure tone?
If it were just a pure tone, you would have no clue.
Or even like combinations of overtones?
So to make Ohm's law a little more precise, what your ear really does is it does bandpass filters. If the components fall very close to each other, you can hear the phase shift. If the components are far from each other, you can't. Even the notes, the second overtone of a fundamental is far enough away that you can't hear the relative phase of it. The frequency components have to be very close together. So you can hear phase only in a very particular case when there's frequency components that are very close to each other, and there's a relatively big shift in the phase of those two signals. Except for that, Ohm's law is true. Okay? The point is just that the Fourier transform, the Fourier series, gives us a way of thinking about a very interesting dimension of a signal, one that separates things that are audible from things that are not audible. So when you're doing signal processing, you can pay less attention to the thing that's not audible. You can go ahead and distort that and nobody will know. But you have to pay close attention to the things that's very audible, which is the magnitude. We'll see at the end of the hour that situation is completely flipped for video. Okay, but before we get there, so the first thing to think about was the idea of circular frequency, the fact that we're looking at frequency responses living on the unit circle rather than on the j omega axis. The second big difference with DT is the frequencies are cyclic. So rather than having harmonics go the whole way up to infinity, as we did in CT we would have a Fourier series constructed of the fundamental, the second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic, the whole way out to infinity, in principle at least. In DT, they wrap so that you get a finite number of them. In fact, you get, if you're taking a sequence of length n, here illustrated for 8, you get 8 possible frequencies, half of which are negative. And you don't care about those anyway. So the number of frequency components for a DT signal is finite for DT Fourier series. That has enormous implications. It means that when you do a Fourier series decomposition, there's a finite number of terms. That's enormous because that means that if you started out with a sequence of length cap n, say 1024, and you take the Fourier series of it in order to think about the frequency content, you can replace the 1024 numbers in time with 1024 numbers in frequency. There's no, well, no is exaggeration. There's a factor of 2 kind of explosion of data because I went from n real valued signals, samples, to n complex valued signals. That's not quite true either because of reasons about how information works. The, how do I want to say it? The resolution that you need for the frequency domain representation is actually slightly smaller. To a first order, you're replacing n with n. Okay, that's really good because if you think about the alternative in CT, you would be replacing a signal with an infinite number. And that's just not reasonable if you want to think about processing signals with digital electronics. There's no way that you could process an infinite number of signals in a finite amount of time. So the fact that you're replacing n samples in time with n samples in frequency really lends itself to doing signal processing using digital techniques. Now, the problem is, and just one way of thinking about the finite length is that you can think about it by matrix. That's just a mnemonic that helps me a lot to think about how if I have a 4-length sequence, you go through some matrix. And what comes out is a 4-length frequency response. You have some 8-length sequence, you go through some matrix, and it comes out some 8-length frequency representation. And there's actually a lot of intuition that you can draw in making the parallels between matrix representations and the Fourier representation, because it is a transformation, a linear transformation, just like the matrix implies. There is one problem with that finite representation idea, and that is that it scales poorly. If you think about having a two-length sequence, the two-length sequence has a two-length representation in frequency via the Fourier series. And that representation has how many coefficients? 4, 2 by 2. Now if I do a 4, I get 4. How many coefficients? 4 by 4 is 16. Now some of these are 1s, right? All of these are 1s. As you make the sequence bigger and bigger and bigger, however, the number of trivial entries gets smaller and smaller and smaller relative. So as you go from a two-length sequence to a 4-length sequence to an 8-length sequence, now we're up to 64 multiplies in order to convert a time domain representation into a frequency domain representation. Well, that's bad, because the kinds of things we want to do are not 2 and 4 and 8. The kinds of things we want to do are manipulations on signals of 10 to the 6th, 10 to the 8th, 10 to the 12th, right? For my doctoral thesis, I did some fluid dynamic problems where the calculations had 10 to the 6th unknowns. And I used frequency domain techniques, which I was able to implement with things that I'll talk about in a minute. If we had used the scaling by the square, it just wouldn't have worked, right? If you have 10 to the 6th unknowns, and if you're using a method that converts from one representation to another that involves 10 to the 12th operations, that's just not a good idea, okay? So that's bad. So by the theory of lectures, what I'm about to tell you is there's a great way to fix this, right? If there weren't, I wouldn't tell you. I wouldn't pose the problem. So the question is how to think about this scaling in order to not have the number of calculations that you need to do blow up with n squared. So in order to motivate this, I've used a funny notation where the w represents the nth primary root of 1. That just saves me from writing out e to the j 2 pi over n 64 times, which when I did it, it didn't fit on one slide, right? I had to compress it too much and you couldn't see it. So just to save space, every time I say w80, all I mean is compute the 8th root of 1 and then raise it to the 0 power. Compute the 8th root of 1 and then raise it to the 7th power. That's all that means, okay? So the idea is there a way that we can think about the structure of this matrix more simply? And in particular, is there a way to use divide and conquer, right? That's our best algorithm. It would be great if we could take the 8-point sequence and substitute in its place finding frequency representations for two 4-point sequences. And by the theory of lectures, that's what I'm about to do. So the idea is, what if I just simply took the even entries in this more complicated problem? So I have 8 entries, none of which are necessarily 0. So I have x0 through x7, and I want to find the frequency representation c0 through c7. What if I just did the evens and the odds separately? That'd be great, right? In order to do them 8 in one fell swoop, I need 64 multiplications. In order to do each of these problems, I have 16 for each. That's only 32. I have a big win. Okay, but now I'm left with, is there a way to relate these things, these A, Ks, and B, Ks, back to the original CK? So the idea then is, how would you think about the contribution of the evens as opposed to the odds in the overall calculation? So think about the even sequences, the even numbered entries in the signal. Think about the transformation if you were to do a frequency representation for that via the Fourier series so that you would get A0 through A3. The first thing you see is that these numbers have W sub 4, the 4th root. I need W sub 8, the 8th root. But there's a simple identity, right? If I know the 8th root, I can just square it to get the 4th root, right? So I can rewrite the 4th root guys in terms of equivalent 8th root guys. Okay, that was trivial, right? Nod your head. Completely trivial. And then I can say, well, okay, here's my problem that I would like to solve. What if I was only thinking about the contribution of the evens? If I'm only worried about the contributions of the evens, then I don't need to worry about some of the columns because they don't contribute to the evens. That's where thinking about things in terms of the matrix helps us, right? We can visualize operations as operations on a matrix. So now if I'm only worried about the evens, I only need to worry about 4 of these columns. And if I squint at this, I can see that W8, 0, 0, 0, 0, that's the same row as up here. So this is the same as that. And this one, W8, so they're all W8s, right? I don't need to say that. 0, 2, 4, 6, 0, 2, 4, 6, 0, 4, 0, 4, 0, 4, 0, 4. These numbers are just the A coefficients. Furthermore, it repeats. 0, 0, 0, 0 is the same as 0, 0, 0, 0, so that's A0 and that's A0. What I just found was that the way the evens affect the answer is precisely by taking their Fourier representation and repeating it twice in time. Well, that's pretty cute. So therefore, the contribution of the 4-length sequences to the 8-length sequences is showed this way. Stack up the frequency representations for the 4, and that is their contribution to the 8. The same sort of thing happens when I do the odds. Now if I only look at the odds, I throw away a different set of 4 columns. And now if I try to compare that to what I have up here for the odds, I don't quite get something as easy. So if I look down this column, they should have all been 0. But if I look down this column, it's 0, 1, 2, 3, 4, 5, 6, 7. If I look down this column, 0, 2, 4, 0, 3, 6, I'm not quite getting the right answers. But it turns out that if I simply factor this number out so that I make the first coefficient right, all the other coefficients are right too. So I've got an easy rule now for how the Fourier coefficients for the odds contribute to the answer for the 8-length sequence. And now all I need to do is glue those two together. So the way I can calculate the 8-length sequence is to calculate the A's and B's from 4-length sequences, and then paste them together this way, and I'll get the 8-length answer. Now, pasting them together takes some multiplies, right? So it took me 16 to compute the A0 to A3. It took me 16 multiplies to figure out B0 to B3. So I'm up to 32. Then I have to do 8 more to make the B's look right. So if I just count multiplies, I'm now doing 40. But that's a win, because that's compared to 64. And I get precisely the same answer. That algorithm, that's an algorithm, right? That's a rule-based system for how you take one set of 8 numbers and turn it into a different set of 8 numbers. That algorithm is called the FFT, the Fast Fourier Transform. That's mostly to confuse you, because it's not a transform. But it is fast. So it's really a fast Fourier series, right? And in fact, the guys who figured it out knew that, and I don't know why we insist on trying to confuse you. That's perhaps our job. But the FFT, Fast Fourier Transform, is really the Fast Fourier series. And the idea is that it's a divide and conquer thing. So if you think about extending it, so I motivated it by thinking about how to calculate an 8 by 8 from two 4 by 4s. But let's start from 0 and say, let's let capital M represent however multiplies it took to get an endpoint FFT. How many multiplies does it take to do a 1-point FFT? If my signal is periodic in 1, so what's the relationship between the series representation and the time representation if the length is n, capital N equals 1? The relationship is identity. If my sequence was 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, which is a sequence that has period of 1, then the series representation is 17, 17, 17, 17, not all that surprising. So it takes exactly 0 multiplies to calculate that one. How many multiplies does it take to calculate a length 2? Well, you do 2 length 1 problems. And then because it's length 2, you have to do those 2 extra multiplies. Then to take a length 2 and turn it into a 4, how many multiplies for 4? Well, you have to do 2 length 2, but now it's length 4. So there's 4 gluing multiplies. To do 32, you have to do 2 length 16, and then there's 32 gluing. When you're all done, it takes n times log n. And the point is that n times log n can be a lot smaller than n squared. Okay? So let's go back to the motivational example. The idea was, what if I had about 10 to the 6th unknowns, right? So that's about 2 to the 20. Yeah, that's right. So 2 to the 10th is 10 cubed, roughly. 1024 is 1,000, right, in CS terms. So I have about 2 to the 20th. So what would be the savings if I did the FFT rather than the direct form n squared? So it'd be, so I need to take 2 to the 20 times 2 to the 20 would be the n squared algorithm. And the other algorithm would be 2 to the 20 divided by 20. It's enormous difference. That's the point. Okay? So just a little bit of historic context. That algorithm has been repeatedly invented in time, right? So we usually cite Cooley and Tukey. They wrote a classic paper in 1965. The title of their paper was An Algorithm for the Machine Calculation of Complex Fourier Series. They knew it was series. That was 1965. That was when computers were starting to get big. They actually went on and solved some very interesting problems, including neuroscience. They were the first people who solved Hutch and Huxley's model for a propagated action potential and showed that the equations that Hutch and Huxley had found for biology actually work. So that was 1965. However, before them in 1942, Danielson and Lanczos had independently discovered it. In 1903, Runge had discovered it. And in 1805, Gauss described it. Now, there's a good reason why all these brilliant scientists, so Gauss noted it and even used it, but he commented on how useless it was. Why would Gauss think it was useless? He was kind of smart. Fourier, so Gauss actually died before he published this, but it got published posthumously before Fourier started to work. So this came before Fourier. So why did Gauss think this was useless? And that's 1805. And now we come around to 1965, and Cooley and Tukey make this huge deal, and they're world famous because of their rediscovery of something that Gauss knew in 1905. Yeah?
I mean, you're not going to be doing anything that's like 128 by 128 by hand anyway. So.
That's exactly right. That's exactly right. So when Gauss was thinking about it, he was thinking about 16 by 16. And so, yeah, you save 2. Big deal, right? He was much more actually impressed with logarithms because he was doing the multiplies by hand. And the log made it much easier to do multiplies because you could substitute addition, right? So he actually commented on how useful logarithms are. And he didn't comment on how useful this is, but now we make a big deal of in the other order. And it's entirely digital computation, right? So when we solve systems of 10 to the 6th or 10 to the 10th unknowns, this is an enormous deal. And logarithms are good too, but this is an enormous deal. OK. So one more piece of theory and then one more ending thing. The piece of theory is going from periodic signals to aperiodic. And not surprisingly, that works just the way it did in CT. In fact, there's nothing new here. We can think about how would you make a Fourier transform compared to a Fourier series. With the CT, we developed the theory for series first because it was easier. And then we derived the theory for aperiodic signals by something called periodic extension. We took an aperiodic signal like this DT signal, made it periodic like that DT signal, and then took the limit as the period goes to infinity. Had we stayed in time domain the whole time, that would be a trivial no-op. But the trick was that after we did the periodic extension, we then took the series of this and then passed the limit on the series. OK, so that's the trick. So we think about generalizing the aperiodic into periodic. Then we take the series. Then we pass the limit. And we ask whether the series converges. And just like CT, the answer for DT will converge. So you start with a periodic signal. You write out the DT Fourier series, just as we've been doing. And you get an answer that for the square pulse looks very much like the answer we got before. The tricky thing that I've done here is I've written the series on two axes, just like CT, a k-axis, which is the harmonic number, and an omega axis, which is the frequency. The frequency represents the position around the unit circle. So capital omega is the angle on the unit circle. Then, if I change the period, the effect of making the period bigger is to put the frequency, the harmonics closer. But in a magical way, because the envelope, the thing showed by the thin black line, doesn't change as I take the limit. That's what enables me to think about there being a limit. As you put more and more, as you make the period bigger and bigger, you get more and more lines in an envelope that doesn't change. And then you can think about the envelope as being a function of the continuous variable omega rather than the discrete variable k. And then you can think about what would happen if you passed the limit. And the idea is that if you do the synthesis equation, there's an ak that depends on 1 over n, which you can write in terms of the fundamental frequency omega naught. And then as you pass the limit, omega naught is the spacing between these harmonics. So if you multiply by the spacing, you get the area of that block. So the area associated with n equals 0 is this area. The area associated with n equals 1 is that one, n equals 2, n equals 3, etc. And so by doing the sum increasingly converges to the integral. So you get precisely the same kinds of formulas we've been using before. The one thing that's a little bit weird, in the DT Fourier series, we had a sum in the synthesis equation as a sum in the analysis equation. Here we get one of both. The DT Fourier transform, that's this thing, is a function of the continuous variable. Discrete-time Fourier transform has a continuous frequency variable capital omega. Because it has a continuous, even though it's a discrete-time Fourier transform, discrete-time Fourier transform has a continuous frequency variable cap omega. So when we do the synthesis, we have to integrate. So one direction it's a sum, the other direction it's an integral. Other than that, it's just the same. Okay, so there's a striking parallel. All of these things are highly related. The DT Fourier transforms are highly related to the DT Fourier series, as is the CT transform to the CT series, and there's lots of connections, and we'll talk about that more next week. how you can infer how one of these transform relationships would have worked from all of the others. For the time being, the important thing is just that when you do the DT Fourier transform, you can think about that just like the CT Fourier transform. The CT Fourier transform was evaluate the Laplace transform on the j omega axis. Now you evaluate the Z transform on the unit circle. The unit circle is no surprise. That's what we've been doing. Because of the relationship between the DT Fourier transform and the Z transform, the DT Fourier transform inherits all the nice properties of the Z transform. We'll make a bigger deal of that in the upcoming 2 weeks. In fact, that's the next 2 weeks of this course, is to figure out the implications of all of those properties. But for today, what I want to just close with is one more example of how you can think about these frequency representations helping you to imagine the kinds of signal processing that you do or would like to do. And so the last example now is one from image processing instead of audio processing. I started with audio processing. Now I want to think about image processing. Image has the property that I'm going to have to do something with 2D, right? And in this class, we primarily think about 1D, but you saw in the zebra problem that sometimes extending to 2D is not hard. And it certainly is the case that in the case that the Fourier methods, extending to 2D is really easy, right? Or at least I'm going to say that. So the way you can think about a Fourier series in 2 dimensions is illustrated by this picture. I took a picture that was 512 by 512. That's the boat. And I made a new picture by taking this row, calculating the Fourier series for that row. That had 512, so it's 512 by 512. So I took these 512 numbers, took the Fourier series, and wrote them here. Then I took these 512 numbers and put the Fourier series here. And repeat, right? So fill the whole thing up. Okay? So I took 512 length sequences. Then I took that string of numbers, took the Fourier series, and put it there. And then that one, take the Fourier series, put it there. Take that one, take the Fourier series, put it there, and build up an image that way. Okay, so I, row by row, took all the Fourier series, pasted them together. Column by column, took all the Fourier series, pasted them together. When you're done with that, you get what we call a 2-dimensional Fourier series. And what you see on the right then, so here's my original picture, 512 by 512. Here's the picture of the magnitude and the angle. You can clearly see the boat. And it's much clearer here. So the phase looks kind of random. So to gain some insight into what's in the magnitude and what's in the phase, what I can do is generate a new picture by setting the angle everywhere to 0. So what I took the picture, magnitude, and I did this to it. I got the magnitude and angle. I set the angles to 0. And that's the picture I got. Okay, so I was able to munge the angle in the auditory thing, and you could barely tell. Can you tell that I've munged the angle? Okay, there's some distortion caused by the angles. There are some things that you can still see, right? So if you go back to this one, right? There's these things here, and there's these things here, and if you go to this one, there's some lines here and some lines. Maybe there's something there, right? But to a first order, it kind of messed things up. So then I did the opposite. Just throw away the magnitude and substitute 1. Put 1 everywhere there was a magnitude. But put the angle back. Now you can almost see the ship. So throw away the magnitude is better than throw away the phase. That's kind of cute. Can somebody think of why throw away the magnitude might be better than throw away the angle when you're trying to look at a picture? Yeah? That's exactly right. So if you muck around with the phase, you're changing the position, right? Even in audio, when you muck around with the phase, you're changing when the component comes out, earlier or later. In the picture, you're changing when the brightness comes out, earlier or later. If you want to have a nice straight line, you better keep all the phases lined up. If you scramble them, they end up scrambled and you don't see them anymore. And as you said, that the magnitude is controlling the intensity, so my intensities are all screwed up. But you can kind of still see the lines. You can almost even read, if you know Polish, you can almost read what the title says. Okay, so one more manipulation. I took a different picture and substituted the magnitude of that different picture in place of the magnitude of the boat picture. So, angle of the boat, magnitude of the mystery picture, and it came out pretty good, right? But by the theory of lectures, of course, you know that the way I did this was to get a picture of a different boat, you know, so that it would be very similar, right? And so that's what the magnitude was. So it doesn't really matter much. So it started with this magnitude and angle. Substitute the mandrel's magnitude, and you get that. So it comes out pretty good. So the idea then is just that we've looked at Fourier representations as an alternative way of thinking about the content of a signal. And for many purposes, like audio and video, that alternative representation is easy and insightful. No class tomorrow. It's Veterans Day. Party next Wednesday.